Now in this module, module 10, we'll talk about measuring the spread about the mean, and specifically we'll talk about standard deviation. You've probably heard that phrase before, um, but we'll really define it here in this module. But let's kind of we don't jump into it right away. We're going to kind of ease our way into it. We're going to introduce measuring spread about the mean. So how far is something from the mean? In the previous module, we talked a lot about median and quartiles and all that. Previously we discussed the spread of a distribution in terms of overall range and also a typical range of values. What we know so far is 1, the range is the distance between the minimum and the maximum values. So it's just what's the lowest value and what's the highest value? How far apart is the lowest and the highest? The other is, one way to represent a typical range is with the interquartile range. The distance between the first quartile and the third quartile is the interquartile range, and they even write the little formula. I don't know if I would call it a formula because formulas sound scary and big and complicated, but it's just the value of Q3 minus the value of Q1. Now we want to develop a way to represent the typical range using the mean. So the above, what we've talked about in the previous module, for the most part we used, this is for using, oops, why'd that get so messed up? Median as the center. So we were just getting so caught up in the details with quartiles and interquartile range and spread, I don't know, all these things, we might have lost track that we were talking about, that all that applies only if we're using median as the center. But now we talk about what if we use the mean. If you remember, that's like the average. Instead of just taking the middle value as your center, which we've been doing for the median, now we're going to say, what if we use the mean? Like with exam scores, we talked about if I measure the center as the average of exam scores, where I add all the scores together and divide by the number of scores, that's the mean. Then how do we figure out how to describe the spread and all that? We will again use the idea of distance, in this case, average distance from the mean. So typically, if you measure the distances of all the data values from the mean, what's the average distance from the mean? It sounds complicated because the mean itself is an average, so that's kind of confusing. What's the average distance from the average? Basically, I'm not trying to confuse it more, but we'll really nail it down in this module. We'll start by comparing and contrasting distributions with different amounts of spread about the mean. This will develop your intuition and an understanding of average distances from the mean. So here's an example. Let's see. We're going to scroll down a little bit here. Okay. Comparing the spread about the mean. So here are 3 distributions. The distributions have the same scale and the same number of data points, so they're easy to compare. Okay. So the 3 distributions, we got A, B, and C. Here's A, here's B, here's C. They all have a mean of 5. But you can see, so notice like in the very leftmost one, count A, that there are 3 values at an x value of 4, 3 dots on 4, and then there are 3 dots at 6. So of course, if you have an equal number of dots at 4, equal number of dots at 6, they average to be right in the middle, which is at 5. But in the second graph here, or plot I guess you could call it, plot B, there are 2 values at 4, there are 2 values at 5. Here are 2 values at 4, here 2 values at 5, 2 values at 6, but they still average to be a 5, which kind of makes sense. And then in the very rightmost, the plot C, let's see, where is it? There we go. Still the mean is 5, but this one is almost most obvious because you have 1 data value at 4, there are 4 data values at 5, and 1 at 6. So they all look pretty balanced, I guess, is what I would think is plot A, plot B, plot C. They're balanced about 5, I guess. We can see this easily without doing any calculations because the mean is the balancing point. There you go. I guess that's why I was thinking balanced. The total distance of points below the mean equals the total distance of points above the mean. Which distribution has the smallest amount of variability about its mean? The answer is C, which we kind of probably thought when we saw it. In C, most of the data is at the mean. There's very little spread about the mean. Which distribution has the largest amount of variability about its mean? I'd say A, because there are no data values at 5. 3 of them are below, 3 of them are above. In A, the data is more spread out about the mean. Relative to A, B has a smaller spread about the mean. Some data points are at the mean and some are at 1 unit from the mean. Okay. Let's see here. To further develop um, our intuition for measuring spread about the mean, we will now compare distributions for samples of different sizes. So here's an example, comparing spread about the mean for different sample sizes. The two distributions below have the same scale, I guess the x-axis and the y-axis, or sorry, just the x-axis from 9 to 12 here, from 9 to 12 here. The mean is at 10, and we see that all the data stacked at the mean, except for 2 data points at 9 and 1 at 12. The samples on the left are larger, 8 data points versus 6 data points. Which distribution has the smallest amount of variability about its mean? In this case, the answer is A. Why? Why is that? Because A has a larger proportion of its data at the mean. 5 out of the 8 data points are at the mean in A, which is 62.5% of the distribution, compared to 3 out of the 6 data points for B, only 50% or half of the distribution. In other words, there's less spread about the mean in A when we consider all of the data.